In this video, we're going to discuss acids and bases. There's a lot of definitions for acids and bases. We tend to think of boiling vats of things in Bond movies that dissolve anything that goes into them. Not really. But there's a lot of different forms of acid and base, and the chemistry is vitally important because if you have a water solution or a water environment, there's going to be acid and base chemistry occurring. And so we cannot ignore that it is happening kind of in the background of almost every other reaction that we do. So what is an acid and a base? Well, let's start with our first definition. Our first definition is the Arrhenius definition. An Arrhenius acid is any molecule that can give away H+. An Arrhenius base is any molecule that gives away OH-. The reason for this is that simplest acid-base reactions involve H+ and OH-. They react with each other and they form water. This doesn't really cover everything, though, because, next up was the Bronsted-Lowry definition. Still, acid's more or less the same. This is something that gives away or donates H+, depending on where you're reading it from. A base is something that consumes or accepts an H+. Why this was needed is, not every base has OH- in it. Ammonia, NH3 here, can react with H+ to make ammonium, one of our polyatomic cations. How do you make that cation? By having ammonia act as a base, in this case a Bronsted-Lowry base. Well, this is the definition that we'll use for most of this course. There's one further, and it comes up much more when you get to coordination chemistry, and that's the Lewis acid and base. Lewis acid and base does away with the requirement that you even need an H+ around. In this case, an acid is something that accepts an electron pair, and a base is something that can donate an electron pair. Iron and carbon monoxide. Iron can accept the electrons in the lone pair from the carbon on carbon monoxide to form a bond. And this is part of why carbon monoxide is dangerous if you breathe it. It binds to the iron in your hemoglobins, blocking up oxygen binding sites, where oxygen would like to be a Lewis base, and as a result, the oxygen doesn't get transported through your blood. This is more important in coordination chemistry, and so our definitions will mostly stay with Bronsted-Lowry. Any molecule that can give away an H+ is an acid. Any molecule that can accept or consume that H+ is a base. Quick examples of acids, things like HCl, H2SO4, HNO3, but also things like acetic acid, usually shortly written as HAC, this is vinegar, or HF, carbonic acid, H2CO3. There's more and more and more. All of these can give away at least one H+. Some of them can give away more than one H+. All of those are acids. Our bases, there's a variety. As we said, ammonia was one of our Bronsted-Lowry bases. Sodium hydroxide, potassium hydroxide, calcium hydroxide. Things that have hydroxides are all Arrhenius bases, but those are also Bronsted-Lowry bases. They give away something that can consume an H+. There are many more, F- or CO3 2-, a carbonate. These can also accept H+. We'll discuss those more in weak acids and bases. But here's a variety of things that can be acids and bases. What's so important about acid and base reactions? Well, anything involving water is prone to involving acid and base reactions because water is both an acid and a base. Two water molecules can collide and transfer an H+ from one to the other. As a result, you get an OH- and hydronium, which really we tend to write as H+ aqueous. In reality, H+ in water can't freely exist on its own. It's just a proton with no electrons. It will stick to the lone pairs of one of the oxygens of a water nearby, forming H3O+. So these are identical. the form of H plus aqueous is the hydronium ion. Depending on your book, you may or may not write it one way or the other. They are effectively equivalent for our purposes. I find it easier to not write in the extra water molecule and tend to use just H+. But they are functionally identical here. And it's an important recognition point. You don't really have H+ free. It is stuck on a water. But this is why it's so important to study acid and base chemistry. Earth's full of water. Life is based on water chemistry. There's always acid and base in water. This naturally occurs. A little bit of water is always doing this. So if you have a liter of water, some of the molecules are slamming into each other and breaking apart. In theory, eventually that hydroxide and H+ can recombine, do the reverse reaction, and go back to being water. But if they drift away from each other at the start, they could take a while to find each other again. And in fact, lots of waters are doing this all over in your solution, and so the OH- and the H+ that meet back up aren't from the same original molecules. It still just takes time for them to run into any of the other ones. As a result, there's an equilibrium. Water breaking apart into the H+ and the OH-, H+ and OH- running into each other to go back. Well, my products are my H+, my OH-. I'll simplify this down. A single water molecule could break apart into H+ and OH-. This all has to be equal to some constant. Acid and base reactions reach equilibrium insanely quickly, so we're never really concerned about Q value. We're pretty much always at equilibrium right away. For pure water, that equilibrium constant is called Kw. It's just a known value at room temperature, and that is 10 to the minus 14. And, well, water's concentration doesn't really change. Not that much water is breaking apart, and a liter of pure water is 55.5 molar water. Losing a tiny bit of that still makes it look like 55.5. Effectively, the concentration of water is constant, so it actually gets multiplied up into the equilibrium constant to become Kw. Constant values don't show up, therefore, in our equilibrium calculation here, and what we find is that 10 to the minus 14 is just the H+ concentration times the OH- concentration. For pure water, every time a water breaks apart, I make one of each, so 10 to the minus 14 must equal some amount of H+ and the same amount of OH-, which is going to be x squared here. What we find is that x, the concentration of H+ or OH- in pure water, is 10 to the minus 7 molar. This doesn't happen a lot. Water's pretty good at being water. Yes, it can give away a proton. It can act as an acid, and yes, it can accept that proton and act as a base, but the reality is it's not very good at doing it. So most of the solution is indeed just water. But there is a little bit of H+ and a little bit of OH-, and they are in equilibrium. So if one of them changes, it changes the other amount. And we can add a lot of molecules that will change our H+ and our OH-. As we saw in our list before, there's a lot of acids and a lot of bases, and when they get added to solution, they will modify our equilibrium here, shifting how much of each of these chemicals is present in the solution.